Recording in progress.
All right, we'll give it a minute or two for people to arrive. Let me share my screen, however. Screen 2. Share. I don't think it shared. You are screen sharing. Don't think that's the right one. Stop sharing. Share. Click, click. Can you see the graphs on the screen?
Yes.
Yes.
Oh, you can, that's odd. I don't get a green border around them, but you can see the graphs. Very good. Well, today we're going to be looking at a couple of dynamic programming examples. Work on this will be given during the week, due the Tuesday when we get back. So you can leave it until next weekend, obviously. I will comment that for many years, Thanksgiving was only Thursday and Friday, and we had classes Monday, Tuesday, and Wednesday, which made the end of the semester quite reasonable. I kind of feel with just 1 week of classes after Thanksgiving, it makes it very disorganized a little bit. Anyway, we have a DAG. A DAG is a directed acyclic graph. So this is a DAG. Write it in, DAG. So no cycles. And what we want to do is find the shortest path from a given node. Now, of course, we do that using Dijkstra, but this method is a lot faster for trees, okay, or DAGs, much faster for DAGs. The first thing we do, and we're all familiar with this, is to do a depth-first search, giving us pre and post numbers. Then when we've done the pre and post numbers, we can linearize. This is also known as a topological sort. And all it is you write the vertices by descending post order. We've done this many times before. This is 14, B is 13, A is 11, D is 10, C is 9, E is 8, and Z is 7. So that's descending post order. It's called a linearization or a topological sort. Then what you do is you redraw the graph after first putting the vertices in the order that we've obtained. So we get S, B, A, D, C, E, and Z. And when we do that, we get this kind of linear look to the graph. So there's the same graph. I mean, the red graph and the blue graph are exactly the same, but you kind of got this flow from left to right. Notice all the edges are flowing from left to right, whereas in the red graph, you've got D going backwards towards C. Now we're ready to find the shortest path, and we do it dynamically. We first of all create the adjacency matrix for the reverse graph, exactly the same as we've done before. So this is the reverse graph. It's just drawing the graph the other way around. There it is. So there's the reverse graph. And now what we do is we systematically move through the graph, putting in the shortest distances. So let me come back and rub this out, because it's got the answers right now. There we go. So is everybody okay with getting up to this point? This is the linearization and the reverse graph. I'll write it down. Linearization. It's a good Scrabble word, that. And then reverse graph. Everybody okay? Some thumbs up? I don't know. I can't see everybody actually. Oh, thumbs up. Thanks a lot. Now, what we're going to do is, starting from the left-hand side, we're going to start putting in the shortest distances. And I can show you how it goes. All right. So obviously, S starts at 0. We'll measure that. Now, let's look at B. B can go back to S for 3, and it's its only choice. So this is 3. That's the distance back to S, and its parent is S. All right. Now we look at A. A actually has 2 choices. It can go to B and then to S. So A is 13 if we go through B, okay? Or if we go through directly to S, it's 3 directly to S, right? A can go back to B. B is 10. 10 plus 3 is 13. Everybody see that? It's just the addition. So if we're looking at A, I'll write it down. We can do the weight of AB. No, I'll do it the other way. It looks very familiar to what we've done before. The distance to B plus the weight of A to B equaling 3 plus 10 equaling 13. Or we can do the distance just S plus the weight of S to A is equal to 0 plus 3 equaling 3. And obviously, this one wins. So we're going to actually write bracket. We're going to put 3 here, and the parent is S. We go directly back to S. So we now got B covered, and we got A covered. We're done with A. We can rub this out. And we can look at the next node, which is D. So we go from left to right. We got D. And D has 2 choices. We've got the distance to A plus the weight of A to D. So we can go to A and then the weight from A to D. The weight to A is 3 plus 2 equaling 5. And we can also do the distance to B plus the weight of B to D. So we can either come this way or we can go this way, and we backtrack to the parent nodes. See, we can go from D back to B or D back to A. And this is distance to B is 3. The distance, the weight of B to D is 1 equals 4. So this one wins out. Oops. Oh. So we're going to put D is going to be 4 and its parent is B, because we can go 1 back to B and 3 back to S. All right, next one. It's fairly simple. And let's look, the next one is C. So let's rub this out. And you can see a computer could do this very easily. We got C now, and C can either go to D or it can go all the way to S. So we got the distance to D plus the weight of D to C, or we got the distance to S plus the weight of S to C. So if we're looking at C, we backtrack, we can go directly to D, or we can go directly to S. So in this case, the distance to D is 4, plus the weight of D to C is 1, so that gives us 5. The weight is 0 here, and coming across is 4. That's equal to 4. So this again wins. So we're going to get 4 here, and is coming from S directly. Okay, 2 more to go. Oops. So we got E. So this is why it's dynamic programming. We're going back and looking at the previous results to give us the current result. So we got E, and E can go back to D, or it can go to C. So we got the distance to C plus the weight of C to E, or we got the distance to D plus the weight of D to E, equals the distance to C is 4, the weight is 5, so this gives us 9. The weight of D is 4, and the distance is 1, equals 5. So this wins. So this is going to be 5, and you're going back to D. Okay, one more. We got Z. So Z dot dot. We have the distance to D plus the weight of D to Z. Or we have the distance to E plus the weight of E to Z. And the distance to D is 4, and the weight is 2, equaling 6. Distance to E is 5, and the weight is 5, equals 10. So this one's out, so this is 6, and the parent is D. And then we're done. We have all the distance. We've measured out the distances and the parent at the same time. So we can actually get a spanning tree, as we did before with Dijkstra's algorithm. We get S. So this is all the work that I've done. Here we are. You can read through this, just going through the whole thing again. Let me draw the spanning tree. So, of course, the computer, you and the computer have to do this for each one. But the bottom line, when we finish all of that, is that we get this, D to Z to E, A, B, C. So there's a spanning tree that we get. Let's go back, just check that it looks good. Ooh, all the way back. See all the work we have to do. Okay, and we see D, E, and Z go back to D. C goes back to S. A go back to S. B goes back to S. And D itself goes to B. And if we check, after doing all that work, of course, as I said, the computer, there we are. Z and E go back to D. D goes to B, and then A, B, C go to A. I think I've drawn the spanning tree. No, I didn't. So the other way to draw the spanning tree, of course, is S goes to A, goes to B, goes to C. B goes to D, and then we get E and Z. So you can do the spanning tree like that. This is 3, this is 3, this is 4, this is 4, E is 5, and this is 6. So you can draw the spanning tree in the conventional way. All right, so this is up on my webpage, and you will get a homework assignment of this. It is fairly straightforward. All right, so what's next on the agenda? It's somewhat similar. In that we do a topology, we do a linearization, but we're going to have to do a little bit more work. Let me bring up what I want to bring up. I think what I have to do is make that smaller. Yep, here we are. So in this one, I'll show you the final project. So here it is. What we're looking for is, again, we have a graph, but what we want to do is create a spanning tree for the graph with the property that no two red nodes are adjacent. This is called an independent set when they're not next to one another. And what you're looking for is maximal
I just want to
independence.
watch this clip back, bro.
Say that again. Okay. So this is a max.
Somebody try one more time.
Okay, so let me show it. By the way, this is
I'm not going to skip this. I'm going to go slow.
Gino Russell, mute yourself.
Sorry.
okay. All right. We're using the biographics toolkit that's built into MATLAB. This has obviously got interest from the bio people. But let me go back to the beginning. Here's our graph. So what we're looking for in this graph is a maximal independent set. I can kind of give it to you. It's a small graph, so it shouldn't take too much to try and draw it. We would think, oops, wrong color. We would kind of think our set would like this. We have those there. We can't have G, but maybe we can have F. We can have E, and then we can have B and C. So that looks like a maximal independent set. But if you can imagine a graph with 10,000 nodes, you're not going to be able to color it directly. But that's the sort of image that we want to get at the very end. So we're going to proceed by, again, doing a linearization. So off we go. There it is. This is exactly the same. We do a post order traversal, get the pre and post numbers, and then put them in descending post number. order. So exactly the same as the previous problem. It gives you a very nice topological sort. There it is, flowing from left to right. Now, in the previous example, we reversed the graph and we started at A because we want the shortest distance of A. In this particular case, we're going to start at the right hand. So it's one of the few examples we start on the right hand and move to the left hand. And let me show you basically what we do. Again, I've done all the work down here, but I want to look at one where we can go back. Worked example. So you get the idea of what we want to do. And let me erase all the bits and pieces. So here's a graph, and we want to create its maximal independent set. A little less obvious what the answer may be in this one, but what we actually do to start off with is we start on the left-hand side, and in each case, we get two choices. Whether you include the node in the subtree, so let me see what we got. Let's do a subtree to indicate. We'll do a subtree in green. So here's the subtree containing L. Here's the subtree containing M. When we're at it, we've got the subtree containing H, I, and I. So if the subtree only contains one node, we can include it in our discussion. So what we can do, let's make this a little bit smaller. Move it up. Let's erase. We're going to work on this particular table. And I think it's fairly obvious that if you've got a single node in the tree, clearly that node is a maximal independent set. Yes? That's all you can do with just one node. It's a single maximal independent set. So I can get rid of the tree. Goodbye. Color it again. Now let's get rid of this tree. And we'll color that one. We'll color that one. And we'll say we're going to, this is going to be, I've got to go back. Hang on a second. We've got to do a maximal independent. Maybe on this one, I haven't done a DFS on this one. Maybe I'll just go back to the previous one because I haven't got a DFS for that one, but I got DFS on this one. So back. All right. So I'm going to use this one. Okay, so this is going to be red. Because I'm going to count it. And I'm going to include you. And if I exclude you, it's 0. So what this says is E, if I include the node, I get 1. If I exclude it, I get 0. Again, I get 1. I get 0. Obviously, I'm going, if I'm drawing the graph, wherever that went, I'm going to have to We got A, C, B, D, F, G, J, I, H, and E. And this is going to be 1, and this is going to be 1, and I'm going to include you. So what this is, where's my table, is L, S, and V. L, S, and the vertex. Let me go through. L is the largest independent set in the subtree. So in E, I pointed out, there's only one subtree. We choose it. So L is 1, and we include you. E got included. All right. Rub that out. I think I'm going to have to choose a different color. How about blue? Yeah, we'll use blue in this case. Same with H. We're going to include you. And the same with I. So we're going to include you. That's 1. All right. Now comes the bit. We're looking now at the subtree nice looking Christmas tree that we got there. And we have 2 choices. We can look at include the node, but if we include the node, notice if we include the node, we can't have the children because all the children are next to it. So we include the node. I only have 1 for the maximal subtree, namely G itself. If I exclude the node, then I can have all 3 children. So this is 3, but I've excluded the node. This is 1, by the way. So if I exclude the node, I can get a subtree with 3 independent sets in it. Can you all see that? Look, in the green tree, I can have 3 as long as I exclude the node. I don't allow it. If I include G, then I only get 1 because I can't include any of the children. So that gives me 1 and 3. So for G, I get, if I include it, I only get 1. But if I exclude it, I can get 3, but I don't count the node. What's a J? Oh, J is 1, 2. G has children, J, I, H. Yeah, it's 3. Okay. I should make sure I got the tree correct. Boom, 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 boom. There's my green. This is the tree for G. Oh, there we go. There's the tree for G. If I count J, I, and H, I have 3 children. They're fine. If I include G, I only get 1. So I exclude G, and I have the size is 3. Everybody okay with this? Exclude G, and the subtree with root G now has 3 nodes. All right, rub it off. Boom, 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 boom. Okay. So this is 1. Exclude. So the top is if I include, and the bottom is if I exclude. You can see that exclude, I get 3. Let's move off to J. So we're now going to look at F. We're now going to look at F, and we're going to decide on whether we want to include it in the tree. Let me draw the tree. So F, we get this tree. There's the tree with node F as the root. And now we've got two choices. We can either include F, and therefore we can include all the grandchildren. 1, 2, 3 grandchildren. Add F, that gives me 4 if I include. So if I include F, I get 1 for F and 3 for the grandchildren. If I exclude F, I can only get G. Well, G has 3, so that's all right. G is 3. Notice G is 3. L, the L value of G is 3. This is the L value. But 4 wins out. So this is going to be 4. And I'm going to include it. There we go. Let's rub out the tree. So notice the dynamic program is working. I'm going to keep going through this. So then we get to D. All right, so we got the node headed by D. And now let's have a look at that tree. I'll draw it. Of course, you don't have to draw the trees. I'm only drawing them for illustration. Here's the tree headed by D. And notice we now got E into the picture. So there's the tree with root D. And we got two choices. Either you include D. If I include D, I get 1. And then I get its grandchildren. Well, it's only got one grandchild, G. So G, we notice, is 3. We get 3 from the grandchild plus 1 from D. So if I include D, I get 4, because I get D and its grandchild, only 1. If I exclude D, I get F, all right? And F is also 4. So we got a tie. Do we exclude? So if we include, we get 4 as a subtree. If we exclude, we get 4 as a subtree. Let me rub out the tree. Oops. And actually show you what's going on from a tree point of view to try and illustrate exactly what this is doing. This is 4, and this is 1. Okay, if I draw the tree D, here it is. I have E as a child. I also have F as a child. And F feeds down to G, which feeds down to J, I, and H. And we've noticed that we've included J, we're including I, we're including A, and we're including F. All right. And that gives us 4 for this one, 3 for this one. This is just 1. So there's the picture of D. And we've got two choices. We can either include D, that gives us 1, plus the grandchild, that gives me 3. So I include D, and I can include G. Or I can exclude D, and I get 1 and 4, giving me 5. Let me see. So if I exclude D, I can have its child 4 and E. So if I exclude D, I actually get 5. Because if I exclude D, I got the child E and I got the child F, which leads on to 4. Notice, you see, so we get 1 and 4 make 5, and you can count them 1, 2, 3, 4, 5. So we're going to go 5, but we're not going to include you. There we go. So let's rub it out. And now you see how the dynamic program is working. Let's have a look at B. B, we got 2 choices. Either you include the child, which is D, which is 5. Okay, so exclude, and we get 5. So D, if we exclude, that's underneath. If we exclude, we get D, and it's only 5. If we include B, I conclude B itself and its grandchild, F. F is 4. You see, so F is 4, and B is 1. So that gives me 5 again. If I'm looking at this, so I get 5 and 5. Let's have a look. So include B, I get F. So they got the 1 grandchild, and F is 4. My F. Include, and include 1, 2, 3. Yeah, so F is the top 1, 2, 3, so that's 4. D is 5, exclude. B is 5. Either way, you get 1 for B, 4 for F. That gives me 5. If I exclude B and F, I get include. We get 5 for D. There's 5 for D. That was the picture. 5 for D. This we get. So I want to check this again. Let's go back to D. I drew it. D, include it, and I get G, which is 3, so that gives me 4. So I'm going to get 4 if I include it. If I exclude it, I get F, which is 1, and I think this is 4 and 4. Let me draw the picture again. D gives you F. F goes to G, R, J, I, and H. So F is 4. Now D, if you exclude D, I just get the child. It's 4. Yeah, so it's 4. My mistake. It's 4. So D is 4, not 5. There it is. Look, 1, 2, 3, 4. If I include D, I get 1 here and down to its grandchild. So either way, I get 4. 4 include, 4 exclude. Okay. If you got a tie, I go with exclude. So I exclude D if you got a tie. Here we got a tie, 4 and 4, so I exclude. Now let's have a look. Move on. Let's have a look at B. If I include B, I get 1 and its grandchild, which is 4. So 1 and 4 make 5. So if I include, I get 5. If I exclude, I just get the child, D, and nobody else. So we get 4. So this is 5 and 4. Notice you see, let me draw the picture to show you what's going on. If we got B, it's got just one child, D. D has two children, E and G, which is going to J, I, and H. So there's the picture with D, with B as the root. And so far we've got this one, this one, this one, and this one. Okay, let's pull it in. This is 4, this is 1, this is 3, and these are all 1, so we can ignore those. So B has a choice. Either we include B, and then we get the grandchildren. So include B, then we miss D because it's adjacent, and we can get the grandchildren, which are 1 and 3. So D, B has grandchildren, G, and it also has grandchild E. There it is, E. Okay, B has grandchild E and G. So if you add the grandchildren up, I get 1 and 3 is 4. You include B, it's 5. So I get 5 for B. Whereas if I exclude it, I only get 4. Because if I exclude B, I only get this one, the child, which is 4. So that's good. Rub it out. So C is 1 and 1, obviously, because it's just a single node. Now let's finish off with A. We got 2 choices for A. A, we can include, but if we include, we cannot conclude C, we cannot do B, we can only do the grandchild, only one grandchild here, D. D is 4, so if we include A, we only get 5, 1 for A and 4 for D. That gives you 5. Notice dynamic, we only work with D, the grandchild, and A. So A plus the grandchildren. So that gives me 5 if I include. If I exclude, I can have C, which is 1. I can have B, which is 5. So if this is 1, 1. This is 6 if I don't include A. So I end up maximal independent set being 6, and I've colored them in. There are the 6 independent set. There we are, rub it out, make it look nicer. So the red is the maximal independent set. And I've actually been able to construct it. There it is. Now, the only warning is, before I finish off, I should go left to right just to see if accidentally I did get 2 red ones next to one another. That can happen. That could, in other words, I'm saying you could end up, when you do the analysis, that one's red too. If you've got a child that's colored, then you have to remove the coloration. Okay, so if a child accidentally gets colored because of a tie, you can get rid of it going left to right, just checking that no child of a colored node is itself colored. And that's how it goes. So all you have to do at each step is choose whether the maximum, so let's explain. When you've got a node and you want to know what's going on, you have the children and we have the grandchildren. So what you do is if you want to color this one, you do this and you add up the values of the grandchildren. So the total of the grandchildren you've computed dynamically plus 1. So 1 plus the grandchildren. 1 plus sum of grandchildren. Or the other option is, I'll get rid of that. Is to exclude. So that would be 0. We exclude this node, but then we can add up the children, because having excluded this node, I can add all the children. So 0 plus sum of children. So each step, I look for the max of these two. If it's the 1, I include and put you in. If it's 0, I exclude and just do the sum of the children. And that's exactly what I've got here. 1's a J. J is 1, 1. All right, so I created this, and that's exactly how we go from left to right. If it's 1, it's 1, 1. Otherwise, you use this algorithm. You look at the sum of the children. We look at 1 plus the sum of the grandchildren and move up from left to right to left. Checking, as I said at the very end, that there are no two that may be adjacent. So if I go back to this particular example, I've got all the computations done. So that's that one up there. So this one. So here's a worked example. I use this graph using the ST version. And I ran it through my code. There it is, maximal independent set. It does exactly the same thing. How are we doing for time? The time is, we're almost out. But this is what I get when I run it through my computer. I think what I can do is draw. Yeah, it's a little bit harder. What I'll do is I'll draw the graph of this to illustrate what this is going on. But if you do this by hand, you get this. And in this particular case, there is a child, K, that if I look at its parent, is also colored. And so I have to decolor it. Let me show you. So J is colored, K is colored, but its parent is also colored. So I have to set it back to 0. And let me just try and explain what happened. Here are these two nodes. L is not covered, but originally I would color K because I'll color it because you get 1, 2, 3. But then we go up to J, and if J has two choices, if you look here, J could be colored or not colored, because J would get 1 plus its child, which is 2. So 1, this is 2, it's got 2 children, so 1 plus 2 is 3, include, or if I exclude J, I'll just get this one, and this is 3. So they both are 3, but in this particular case, I want to exclude J because I've colored J. I exclude K because I colored J. So you just have to go through, if you're drawing it, and you get 6. And if you look at this, you get 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 showing up. Okay. And you say, okay, what if I did color J? Well, if I did color J, I would have to get rid of this one because I can't have two together. So I would have to get rid of J. So I introduced K, but I needed to get rid of J. So that's introduced 1, dropped 1. So in this particular case, as I said, we'll drop J, K, we'll drop K and leave J. You could do it the other way around. I could drop J and include K. That's the choice that you get when you are going through the nodes one at a time. All right. Oopsie. So as I said, at the very end, you could have K colored, but you can't have its parent colored and it colored. So one has to go. It's either J or it's K. We're actually going to get rid of K, and there it is. It becomes 0. It doesn't affect this number. This number is going to be the same. I just said it's the same 9 that you get when you have the choice like that. All right, I'll actually try and put a better image of this on. This will be on the homework. Homework on this stuff will be due on the Tuesday you get back, so you still got a chance to ask me on the Monday if you're still struggling on it. As I said, I wrote the program for max independent set. It's right here. It's not hard to write the program in MATLAB, sorry. Then I used the biographic toolkit that exists in MATLAB and was able to come up with this very nice looking picture. So bottom line is we do the topological sort in both examples I gave you. So this week's homework will consist of the packing problem plus these two problems. I'll throw in a baby topological sort, and I'll go back and try and give you a simple example of using a heap for doing Dijkstra and Prim's algorithm. So that's coming up. I'll put the homework up there. Do the Tuesday we get back. On the Monday we get back, there'll be a TMQ, of course, and we'll be finishing up with looking at 1 or 2 things that I want to get done. Don't forget, we still got 4 lectures to go. That's significant. So we will be doing a couple more topics, 1 more homework, and then we'll be done with the semester. All done? All right. So no new homework until this due until the Tuesday we get back. But I'll give it to you. It'll be on the web page by this weekend. By Monday, the new homework will be up there. But you can hand it in, as I said, on the Tuesday we get back from Thanksgiving. Any questions at this point? This is a pretty neat algorithm. And let me say, if you want to become very rich and very famous, cover a picture on many magazines, if you replace this graph, which is a DAG, if you replace a tree actually, if you replace it by a regular graph, so you replace this by a regular graph, it's an NP complete problem. In other words, if you would solve it for a graph, you would get n equal to NP, and you would get $1 million prize and become very, very famous. That's for a regular graph, not for a tree. All right, then. See everybody after Thanksgiving.
Professor Hughes,
Yeah.
Hi, Professor Hughes. I emailed you
Yeah,
about.
your name's on the list.
Okay,
Okay.
great. I just wanted to make sure you received the
Yeah,
email.
no, name is on the list. I've got Alex, I've got you, I've got the student you saw helping Alex and Tim.
Uh-huh.
Tim's leaving. So I got 3, and I still need a 4th, people. So I'll probably see one more because we got 110 plus.
Okay,
So it's a lot of students.
that
It's-
definitely is.
yeah, we keep growing. Anyway, these little examples I gave you, which are not in the book, I mean, they're sort of in the book, but they're not described very well, are very important. They actually are being used. As you saw, bioinformatics toolkit, they're actually being used out there in the real world. Okay. And as I said, if you want to become very famous, just choose a graph, not a tree, but a graph, and try and do the same thing. It's an unknown problem. Not only is it unknown, it solves the n equals np problem. So you would get millions of dollars and become very, very famous. All right. See everybody. Have a nice Thanksgiving.
Did you take attendance?
No, I assume people, I mean, people going home. So I've got the notes for this. I write out so people can read through my example. It's not as good as seeing it by hand, of course, but it's doable. You can do it. All right, I've worked through this one very carefully. I assume we got the dynamic. Here we are. There it is. So you can do the same thing with this one that I've just done. And I think we got one in between here. That's the difference between what I gave you and the one I'm doing. Otherwise, it's pretty good. All right, then. See everybody on the Tuesday. I'll go through this again on the Monday, and I'll see everybody on the Tuesday. All
Thank
right.
you. Happy Thanksgiving.
Yeah, happy Thanksgiving, everybody. Let me do the end share, wherever it is. Stop share. And what on earth is going on here? Stop lighting. All right, leave.